Alright guys, welcome back to Psych 300. I got a feeling that moving forward, these little lecture videos are going to be just a little bit iffy in comparison to how useful they were before, simply due to the sheer amount of math. But that only really applies if you're listening. If you're watching the screen, it might actually not be too bad. But if you are just listening, I'll try my best. So let's look at this content here. This is going to be on normal probability distribution. And to enter that, we look at statistics as a whole. So what are statistics? Statistics are the sets of procedures and rules for reducing large masses of data to manageable proportions in order to draw conclusions from those data sets. Right? Take the big, make it small, do it well, essentially, when it comes to numbers and data, right? So there are two ways that we do that. There are two types of statistics. There are descriptive statistics and there are inferential statistics. I can't talk apparently. Descriptive statistics are concerned with and are the numbers that summarize and describe data. Again, they simplify large data sets into meaningful numbers or visual summaries. Right, the examples we looked at in class, right? 45 is Lotto 649's most frequently drawn number. The age range for the 2024 Paris Olympics was 54 years. Ernie's 2025 postseason batting average was 0.643. Again, it's telling us what the data looks like. It's giving us our numbers, our meaningful numbers, even if it's a visual summary like a diagram, but it's not telling us why that is the case. Um, Yeah, it's not elaborating at all. It's not drawing a conclusion. It's not making a generalization. It's just kind of presenting us with a thing, right? Telling us what the data looks like, but not why. That's descriptive statistics. Inferential statistics, however, are concerned with and are the calculations that allow drawing conclusions and making generalizations beyond the observed data. So, inferential statistics are used to infer population characteristics from sample data, for example. Right? Examples here are like people rate their own voices more attractive than others rated. Children with better verbal skills at age 12 are more likely to have drinking problems at age 24. There's a generalization, there is a conclusion involved in the inferential statistics. Right? It's providing us with more information, not just literally giving us what the thing is. So that's the difference here, right? The key to inferential statistics is the normal distribution, because most inferential methods assume or rely on normally distributed data, at least to a degree. And that's what we're going to be looking at here. So let's look at normal distribution. If you look at the screen, effectively this is an example, right? A normal distribution is a probability distribution where the data is symmetrical and bell-shaped, and most values cluster around the middle of the distribution, right, the mean or the center. This is in the average range, right? If you look at the examples here, we have our high and we have our low, but most of the data is clustered around this average range here. As the lower you go towards each side, towards the extremes, towards the high and the low, the less values occur, right, in those tails. When you're randomly picking a value from normal distribution, you're more likely to get a value near the mean than the extremes, and this reflects how population density, or probability density, sorry, is distributed across the curve. Again, you are more probable to get something around the center area than as you taper off on each side. If we look at this, we can look at how we use this normative curve as a chart for distribution. The curve can show us where values are relative to other values, allowing us to use, for example, in this case, the height and positioning of a curve, along with what's along the x-axis, to determine the frequency of values occurring and how many values are above or below a certain point. Above meaning to the right, and below meaning to the left. So essentially, this is just describing how we read these charts, right? We have an x-axis kind of describing a number, or a range of numbers, and then on the y-axis we would have a frequency, right? Frequency of occurrence, and that would be describing the occurrence of numbers as you get, above or below a certain point. Yeah, so I think we have an understanding of what normal distribution generally looks like. Again, fundamentally, it is symmetrical and bell-shaped, and most values cluster around the middle, and we understand how to read it. The characteristics of a normal curve, right? These normal probability distributions, these normal curves, go as follows, right? This is how we identify normal distribution. So the three properties, the three characteristics for the normal curve, is that the central tendency is unified. It is symmetrical, and we have kind of like known fixed areas. I'll get into all of these. So the central tendency unification here means that in normal distribution curves, the mean, the median, the mode are all the same. If you know one, you know the rest of them. They're the same value. The average of the data, the most frequent piece of the data, and the middle point of the data are all the same. That's the benefit of these normative curves, right? When it comes to being symmetrical, half the data lies on each side of the mean, or in the middle here, in the average. It's going to be the peak of the curve, right? Because it's unimodal. So technically, it's lying on each side of the median and the mode, but we're going to go with mean because it's the average there. So half the data lies on each side of it, right? The curve should represent two equally split mirror images of the other. And finally, when it comes to the areas that we know, the proportions, which also refers to areas, right? We're not talking about like, well, I guess technically we are talking about literal area of the curve, but we're talking about the different proportions, right? The proportions under specific sections of the curve are mathematically fixed. That's a benefit of normal distribution here. You will have a mathematically fixed area purported to each section of the curve, and we'll talk about that a little bit more. But just a thing, again, when we say we're trying to find the area under the normal curve, we're really talking about finding the probability or the percentage of scores that fall within a certain range of values. For example, the area between the mean and one standard deviation, at least we'll see in a second when we talk about the empirical rule, would be 64. So that, again, that is the percentage of data falling between the mean and one SD. That would be the area, right? And that would be 64. Yeah. Again, as far as symmetry goes, 50% of the values lie on one side of the mean. We know this. You have a probability of 0.5 or 50% of selecting a value either above or below the mean. The area under the curve as a whole represents probability, equal to 100%. And then that 100% probability of the area under the curve as a whole is split into equal components. And we'll talk about what these components look like in a second when we take a look at the empirical rule. So the empirical rule is also known as the 98, 95, 99.7% rule. The empirical rule describes how data are distributed in a normal curve relative to the mean and the standard deviation. It states that, and this is fundamental, and this is kind of what we were talking about when it came to our known areas and how they're kind of segmented and fixed. The empirical rule states that 68% of the values lie within one standard deviation of the mean. 95% in total of the values, remember cumulatively, lies within two standard deviations of the mean, and around 99.7% of the values lie within three standard deviations of the mean. And if you look at the screen here, we can see a clear representation of this. So again, the mean is just x bar here. You go one standard deviation over, and it becomes x plus or minus, or mean plus or minus a standard deviation. You go a second standard deviation over, and you get, the x bar, the mean, plus or minus 2 standard deviations, and then 3. Remember, a standard deviation progression doesn't have to be, a positive interval above the mean. It can also be below it, right? That's why I keep saying plus or minus. A standard deviation generally is encompassing one standard deviation on either side. So again, if you look at the screen here, we have the mean, and then we have all of this is one standard deviation. And on each side, it's split up. So each side of this, like we talked about before, each side of the mean is segmented above or below into 50%. Cumulatively, it's 100%. So one standard deviation is going to be 68% because one standard deviation worth of segmentation in the area above or below is each worth 34% respectively. So that's why within one standard deviation, we have 68%. And then naturally, as we talked about, most of the numbers are centralized to this average area. So the further away you get, the less numbers you have. That's why when you get into a second standard deviation over, on one side it's 13.5%. Cumulatively, it's 27%. And if you add all of that together, the 68% of the first standard deviation, and then the 27% of the second standard deviation over, you reach 95%. And then if you go one more over, we have 2.35% respectively on each side. If you get 3 standard deviations over, in total, you'll be at 99.7%. Yeah. And then everything after that is just kind of small numbers. But we'll never really be able to get exactly to 100 because in theory these lines go on forever, the tails. So yeah, again, the empirical rule is just 68% is within 1 standard deviation, 95% is within 2 standard deviations, and 99.7% is within 3. And then after that, it's all small numbers that go on forever and will eventually add up to 100. Yeah. Okay, so this is when we get into some that we start getting into some examples. But before we do that, it's important to note that while we're going to be using the empirical rule for a while here with a lot of these examples, it's important to note and to point out that what we're effectively comparing here is the operation on normal data distribution with the empirical rule versus with z-scores and z-tables, and we'll get into what those are later. But again, we're comparing kind of two kind of operations on normal data distribution. The first kind of operation is by using the empirical rule, and the second kind of operation is by using z-scores and z-tables. We're still trying to find the same thing when we do that, which is the area under the curve, or the probability or percentage of people, for example, within a certain range. But the method changes because the empirical rule is more of a rough shortcut for typical whole number distribution. And standard deviation intervals, right? Plus or minus 1 standard deviation, plus or minus 2, plus or minus 3. While z-scores and z-tables are the precise mathematical tools that we use for any specific value, right? Even ones like 6.0 hours or the 5th percentile, right? We talk about percentiles a lot. There can be some interplay between the two, and we'll explore that. But again, we're kind of the point of this lesson is to compare these two different methods to finding the area. It just, the difference is when we have the opportunity to use the empirical rule, we will, and it's a lot easier to use when we have typical whole standard deviation, right? Plus 1, plus 2, plus 3, minus 1, minus 2, minus 3. And z-scores and z-tables are used when we need to be a little bit more precise, and we're not just trying to average into a range, and it's more we're trying to find a particular number. Yeah. Okay, so let's take a look at a couple questions here. This is where it's going to get a little bit complicated. I don't know if I already mentioned this, but this is where it's going to get a little bit tricky because again we're looking at some math here. But drown out the noise and lock in. Okay, so using the empirical rule in a survey conducted by Stats Canada, the sample mean height of women in Canada ages 20 to 29 was 64 inches with a standard deviation of 2.71 inches. The question asks us to estimate the percent of women whose heights are between 64 inches and 69.42 inches. So the question is, again, what percent of women have heights between 64 and 69.42 inches? This is real easy because drowning out all the noise from the question, again, we just have our question. We got to find what falls between 64 and 69.42. We know our standard deviation and we know our mean. And this is where you start to find some of the benefits of when you can use the empirical rule, because again, due to the fact that we have our mean and we know that the mean is sitting on 64, and because the data is so symmetrical and evenly distributed, we can evenly divide the bell curve here by the standard deviation, and it fits accurately. Essentially, again, because it's a bell curve and we have our standard deviation, we have our mean, we can easily graph out the different portions here to find our answer. So ignore all that and just look at the screen. if we're asked what percentage of women are between 64 and 69.42 inches, we can easily establish that 69.42 is 2 standard deviations above the mean. Why? Because everything is so evenly distributed and we're looking at the empirical rule. We can just look at 64, and if we add 1 standard deviation over, we will be at 66.71, right? 64 plus 2.71. That doesn't include 69.42. We go another standard deviation over, and we end up at 69.42. Again, we have our mean, which is 64, and we can evenly standardly deviate 2 to the side, 2 to the right, 2 above, technically all the different terms, and we end up with exactly our answer. So we can determine by just taking a look at the 2 sections of the bell curve that we used, which would be, again, we were only on one side. We were looking at the right side here. We set it at 64 at the mean, and we went to the right. We used 1 standard deviation over, 2 standard deviations over. That would be 34%, again, because the middle section is 68% in total, and we used 1/2, plus 13.5%, again, because these 2 standard deviation over sections are 27%, and we only use 1/2 of that. So we have 34 plus 13.5. So we end up with 47.5% of women being between 64 and 69.42 inches tall. Again, the answer 34% plus 13.5%, or 47.5%. Yeah, the way that I described that's a little bit complicated. If you look at the screen here, I'll just leave it on this a little bit. It's fairly simple when you have questions like these, right? We're starting at the mean. We know the mean, we know the question. The question is asking us essentially to just start at the mean and evaluate the percent lying within a number of standard deviations over. So it's very easy. Okay. Everybody good? Everybody good on this one? That's example 1. Example 2. Same qualifiers, but the question is what percent of women have heights between 61.29 and 69.42 inches, right? The mean is still 64 inches, but what does that mean? That's so punny. That means that because we're looking at a range that is below the mean, we're going to have to look at we're not just only looking at the right side of this distribution anymore, we're also looking at the left side. Luckily, again, because we can use the empirical rule here, because the distribution is so perfectly bell-shaped, we can use that. And we can use it to see that 1 standard deviation to the left of the mean is that 61.29. Right? We're looking at that percentage between 61.29 and 69.42. So now we just increase the scope of our math. So instead of adding 34 plus 13.5 and saying that percent of women fall in between these standard deviations like we did before, again, with the mean plus 1 standard deviation over, plus a second standard deviation over. Now we're going to look at the mean, and we see that if we go 1 standard deviation over both above and below, we are looking at a range of 61.29 to 66.71. We increase that by 1 more standard deviation, we end up with 69.42. So our math ends up being 34%, which is the 61.29. Then go 1 standard deviation over, you end up at the mean, and you end up using that whole area, right, which is our 34%, plus 34%. And then you go 1 more standard deviation over, and we end up at 13.5%, or 81.5% in total women between 61.29 and 69.42. All right. I'll leave it on this for a second. Everybody can look at it. Let me zoom out a little bit so that you guys can see the question. Yeah, right. So when we have questions like this, where we're looking at a bell curve, we're looking at a bell-shaped distribution, and we're asked to find data lying in between ranges that are perfectly described by the question, and again, everything is distributed symmetrically, we can very easily use the symmetrical rule to determine what our numbers are going to be looking like. The conceptual insight here, just to kind of qualify that again, right? Since 68% of the distribution value lie within one standard deviation of the mean, the probability of selecting a value at random that lies within one standard deviation of the mean is approximately, again, 68%. The probability of selecting a value that lies within two standard deviations of the mean is approximately 95%. Within three standard deviations, it's approximately 99.7%. Again, the area under the curve is equal to 100, and it represents all possible values. Thus, again, when you're within one standard deviation, it's 68% because that's 34 plus 34, one for each side. Within two standard deviations, it's 95% because that is your 68% from the first standard deviation plus 13.5 plus 13.5, one from either side. Then, when you have three standard deviations over, we have 99.7% because we're looking at our 95, which is the added of all sides from first and second standard deviation over plus 2.35 plus 2.35, one from either side. We can never get right to 100. I guess technically if you went on for infinity, you might be able to, but it's, yeah, don't bother with that. Again, the ease of the fact here is that when we have a normal bell-shaped curve, the empirical rule allows us, at least most probably, to randomly select a value and or find a value without much complexity. We can very easily estimate the likelihood of events, determine the probability of a thing, whatever it may be. But the question is, what if we wanted to use the empirical rule to find the area under the normal curve, right? As opposed to just selecting a value within a range, right? What do we want to find that area? So finding the area under the normal curve using the empirical rule is what we're going to be looking at next year. So the question, applying the empirical rule to this example of sleep, the question here is, over the last month, how many hours of sleep did you get on average? Let me zoom in a little bit just so that it's a little bit more to the people looking at the recording. The data that we have, let me zoom in a little bit more. The data that we have lets us make an inference about a broader population, right? What percentage of people get more than 8 hours of sleep per night? The mean that we have is 6.88. The standard deviation is 1.126. But yeah, so let's, we have this broad question, but let's make a question out of that, right? So let's look at this question. What percent of people sleep more than 8 hours a night? So what we would do here, the empirical method again, we would take the mean, which is 6.88, and add the standard deviation until we reach a number that is 8 or higher. In this case, it takes one standard deviation over, which gets us to 8.006, right? Just above being one standard deviation over. So now we want to see what percent of people, again, what percent of people sleep more than 8 hours. In order to answer the question, we look at what the percent is above one standard deviation point on the graph. So one standard deviation over will put us at 13.5, and then we would add what's left. In this case, we take 13.5 plus a 2.35 plus 0.15. Again, just from being one standard deviation over, two standard deviations over, three standard deviations over, or sorry, we would only take the 13.5 and the 2.35 and the 0.15 because of the fact that being one standard deviation over is within the range, and we're trying to look at what's above that. Right? If we did all that, our answer would be 16, meaning around 16% of people get more than 8 hours of sleep. So I'll leave this on this for a second here, and everybody can look. Yeah. Okay. The issue with the empirical rule really is when we're trying to find the standard deviation and It isn't so, sorry, is when what we're trying to find isn't so cleanly differentiated by standard deviation, right? The issue becomes more apparent when we're looking at percentiles, which we'll do in a second. But again, uh, the point in this question is yeah, we're able to take the, just one second. Sorry. Um, yeah, so we were able to, again, we're looking at what percent of people sleep more than a certain number. We have our range of hours of sleep per night. Again, in this question, we're looking at between 4 and 10 hours. Yeah, so we take the mean, which is the general amount of sleep, the average here, the mean, and we add a standard deviation. We go over and over and over until we are at 8+ hours. And then with the one standard deviation that we went over removed, if we went one over removed, we look at all of the remaining data. So again, we had the mean and we went one standard deviation over. So at least 34% of people from the mean are within the mean to 8-hour range. So we exclude the 34%. But then we are above 8, right? We're just above 8. So now we look at whatever numbers are left within our second and third standard deviations over and what's left, right? Yeah. Yeah, and then we add all of that up. Yeah, and then we'll look at again that question. The issue with the empirical rule is that when we're trying to find when what we're trying to find isn't so cleanly differentiated by the standard deviation, right? In this case, it wasn't perfect, but it was almost there, so that's fine. When we don't have that, the issue becomes more apparent, and that's when we got to start using a different approach. And it's really clear when we're looking at percentiles. Okay, right. So just coming back up here, just a little review before we really get into the alternative to the empirical rule here. Looking at that conceptual insight again, just to reiterate, the area under the curve, again, as we know, it's equal to 100%, representing all possible values. Within one standard deviation, right? Within one standard deviation is 68% because of 34 and 34 on both sides. Within two standard deviations is 95% because 68 plus 13.5 plus 13.5. Within three standard deviations, you're looking at 99.7% because of 95 plus 2.35 plus 2.35. And within four standard deviations, you're looking at 100% because 99.7 plus 0.15 plus 0.15. Again, we can never get right to 100, but we're pretty much at 100. Anywho. Sorry, I had just paused the recording so I could go to a lunch, and now we're back. Yeah. So we looked at applying the empirical rule when it came to that sleep example. But again, just like we had mentioned, and I know for you guys, you probably just heard this, but for me, it's been a while. The issue with the empirical rule really is when what we're trying to find isn't so clearly differentiated by those standard deviations that we talked about before, even a second ago. The issue becomes more apparent when we're looking at percentiles. So it doesn't only apply when we're looking at percentiles, that's key, but it becomes very apparent when we are, and that's why we're going to use it as an example. So let's look at the sleep question again, right? When it came to the, how long do I talk about this, by the way? Okay, it's not too bad. When it came to the sleep example, remember, before we were just talking about, we were looking at how many people slept more than a certain amount. But now the question, let's look at a different question here. Say you get 6 hours of sleep a night, what percent of people get more or less sleep than you? Right? Another question, how many hours of sleep represents the 5th percentile, right? And how many hours of sleep do 5% of people get to get less than that? How many hours of sleep do 5% of people need to get less than that? Yeah. So we're gonna be looking at these questions quite a bit, and eventually we're gonna solve them. But for now, let's take a look at this. Right? If we try to apply the empirical rule, we'll very quickly realize in questions like this, determining the answer can be quite difficult. Yeah. So we understand the question that's being prompted, but the issue is because the data that we're looking for is so specific, because all that the empirical rule really does is present us with kind of like a range, and then allows us to get an approximation. We can't really do much when the question that we're asked is a little bit more precise, right? For example, again, at what value of x would there be 5% to the left and 95% to the right, right? 6 hours of sleep, in this case, is x minus 0.78 standard deviations. How much of the curve is below that? So that's kind of like the two questions that are being asked here. If you don't quite understand what I'm saying, just look at the screen. It's, we have questions here. The original question that we had looked at, and we kind of have this narrowing down of what the question is asking. Right, so how many hours of sleep represent the 5th percentile? At what value of x would there be 5% of the left and 95% of the right? So you get 6 hours of sleep a night. 6 hours of sleep is x minus 0.78 standard deviations. How much of the curve is below that? So essentially, how can we know the area, how much of the curve is below, once we already have the value of x? So these, it's a different style of questioning. Anyway, all of this can be found via z-scores and z-tables, and we'll get into this in a second. Okay, but first let's transition into using these z-tables. Right, let's look at the normal distribution formula. So considering the questions we just asked, again, there are formulas to solve this, but it sucks because extensive math can be gross. While it's rarely used by hand, the full equation is this kind of like f times x equals, and then a big exponent and some rooting and all this stuff. Again, the point is that psychologists and researchers don't really calculate this manually, these questions manually. They instead use pre-computed tables, which are our z-tables, or softwares like SPSS, which we used in our lab, or Excel, whatever. And they automatically compute probability. So, let's look at z distribution first. Right, kind of like what we're talking about when we say that. So let's take a step back, right? Just before we start really looking at z-scores, like we know, up until this point, we've been using the empirical rule for approximating areas. This, like we've said, works really well with bell curves and or curves that have data similar to a bell curve. The standard curve or reference for all of these curves that we've been using, all of these bell curves that are perfect for these standard deviation calculations, are called standard normal distribution curves, right? So in these standard normal distribution curves, for example, the area is 1, right? It's all equal to 100. It is a normal curve that has been mathematically standardized so that the mean is equal to 0, the standard deviation is equal to 1, and the total area under the curve is equal to 1, meaning the entire probability of the space is 100%. All normal distributions can be converted into this standard form, allowing universal comparison across different data sets, right? So this idea, can you guys hear that dog barking? I'm gonna close my window. This idea of our normal distribution curves and the allowance of the empirical rule is in reference to the standard normal distribution curve. Yeah. Because the information is standardized, we've been able to create z-tables with the value of each z being calculated using that horrible formula that we looked at above. Yeah, and it's all kind of used to define a bell curve. So if we look at what a z-table is, we have an example here. It's a table with pre-calculated areas under the curve up to each value of z for a standard distribution, right? Where mean is 0 and standard deviation is 1. Z-score, essentially, is the number of standard deviations away from the mean. And we'll talk about this later. We'll talk about z-scores in particular. But as far as the table goes, how do we read this? Well, each value tells you the area or the probability under the curve to the left of that z-score. So what does that mean? What is the area under the curve for z equals 0? Well, let's find that. If we look up here, under the z tab here, z is 0. Yeah, z is 0, and so here we can see the larger portion and the smaller portion of the distribution here, because z is 0 and the mean to z is 0. We're just right on the mean. So the smaller and larger portions are both 0.5 or 50%. It's perfectly in the middle. But what if the area of the curve or under the curve for z equals 0.31? Well, let's go find that. So if we find the score of 31, or 0.31, I guess, uh, all of the cases to the left of that point or below it make up 62.3%, 62.2%, or 62.17%. That's all the cases to the left. We can see in the table right here, and all the cases to the right of that are sitting at 60 or 30, 37, 38%. Yeah. If we wanted a formula for which that would represent the probability of the z-score here, would just be p times z is smaller than 0.31, but that's not too important. It's essentially just a formula representing what we're finding in the table, which in line with the table means that 62.17% is below the point, the z point here. Yeah, I think we understand that. When you're trying to find a z-score, if the value you're looking for in an area smaller if the value that you're looking for is in an area smaller than half the curve, look at the smaller portion column of the table. If the value that you're looking for in an area is larger than half the curve, look in the larger portion column, right? So up here, if we're looking for the larger portion here, we're going to want to look in the larger portion column in the table. If we're looking for the smaller portion, we're going to want to look here. Yeah. But again, usually, because we're always finding what's on the left of the z, in a case of this, for example, what we're looking at right here, we would rarely be finding the smaller position here. We would be looking for the larger position here in particular. Anyhow, yeah, that's kind of like a broad overview. Just give me a little bit, and we'll get more into z-scores in particular. I think next we're talking about z-scores in particular. But let's look at some of the properties of standard normal distribution, right? What do we have here? I don't actually... are we just analyzing this? Okay. Oh, I see what we're doing. Okay, so here... No, you know what? I still have no idea what the point of this slide was. I think it was just saying if the z, for example, is negative 3.49, we're essentially looking at close to a 0% probability, right? The area of that is almost 0. If we look at the standard distribution, remember it's 0, 1, 2, 3 standard deviations on every side, and we're sitting at negative 3.49. That's way into the outliers here. It's close to 0. As z increases, the cumulative area increases, again, because everything on the left of z is what we're looking at. So as z increases, it gets further right, the cumulative area that we're looking at increases. Yeah. So if we're looking at plus 3.49, we're pretty much looking at almost all of the data, right? Versus negative 3.49, that's almost none of the data. I know that was confusing, but just look at this image. I'll leave it here for a second. You'll kind of understand what it is that it's trying to say. Okay. I assume that it is understood. Can I turn off these notifications for a second? Yes, I can. Okay. Again, everything that we've looked at so far when it comes to the z tables and stuff, again, This begs the question, what happens when we don't have a standard normal distribution like we've been looking at? What happens when we have a non-standard distribution? This means that our mean isn't 0 and our standard deviation isn't 1. Uh, yeah. To find the answer to yeah, let's look at this here actually. This example in the sleep question, again, this data. Um, yeah. So again, what happens? What happens when we don't have standard normal distribution? What happens when we have non-standard distribution? What happens when our mean isn't 0 and our standard deviation isn't 1? Well, we can use z-scores and we can use z-tables. So from this point forward, we're going to be using z-scores and z-tables to kind of work on these standard these normal distribution charts. Yeah. So let's get into it. I know that this one section in particular has been quite confusing. I apologize. Okay. So z-scores, right? A z-score represents the number of standard deviations a raw score, or x, is from the mean. Revisiting that sleep data question again, let's use z-scores to find the area under the normal curve. Remember the question in this case, and we're going to look at both of them. Right, the questions, say you get 6 hours of sleep a night, what percent of people get more or less sleep than you? Which is essentially asking how much of the curve, if we know what x is, how much of the curve is below that, and how many hours of sleep represent the 5th percentile. So at how many hours of sleep do 5% of people get less than that? So in terms of the 5% question, we are looking for the value of x, right? We're looking at the value of x if we have 5% of our value of the area to the left of that and 95% to the right of that. And as far as the 6-hour question, we are not looking for x, we are looking for the percent there. So those are kind of, we'll revisit these questions. These are the questions that we're answering though. But as far as calculating the z-scores goes, any value can be transformed into a z-score by using the formula of the z is the value or the x that we know minus the mean, right? So you do that first, x minus mean, over the standard deviation. Yeah, right? Uh, when it comes to interpreting z-scores, a z of 0 means it's at the mean, a z of plus 1 means it's 1 standard deviation above the mean, minus 1 is 1 below the mean, a positive z means that it's above average, and a negative z means it's below average, right? Just above or below the mean to certain standard deviations. Z-scores allow comparisons across different scales, right? Sleep hours versus test scores, whatever it may be. Now let's look at what we actually do, right? We understand a formula, value minus mean over standard deviation. But let's look at some examples here, right? Let's look at an example of converting raw scores to z-scores. As far as the application goes, let's say we have a random sample of 3 hours of sleep scores, right? 3, 5, and 8. If we know, in this case, that the mean is 6.8 and the standard deviation is 1.125, we can simply plug and play our values into the formula that we just looked at, right? The z is equal to the value minus the mean over the standard deviation. So if we had a random sample of 3 sleep scores, 3, 5, and 8, we would repeat this process for each score, 3, 5, and 8, making their z-scores, again, 3 minus 6.88 over 1.126 is negative 3.45, or 5 minus 6.88 over 1.126 is negative 1.67, or 8 minus 6.88 over 1.126 is 0.99. Again, we have all of these values. We understand converting raw scores into z-scores. Yeah. So, let's say we were given the same question as above, right? Let's say we were given that question. Say you get 6 hours of sleep a night. What percent of people get more or less sleep than you? We can use the principle above, converting the raw scores to these z-scores that we just talked about to figure that out. So, plugged into the formula in that question, x would be 6, right? We have our x, we have our number. 6 minus the mean, 6.88 over 1.126. The z would then be equal to negative 0.78 standard deviations below the mean. And again, the question mentioned that. So to answer the question, how much of the curve is below negative 0.78, we would do this. So, and I know technically you can do the math, but we're going to use the z-table, okay? So first, let's take a look at our curve. If we aren't looking at a literal curve, but instead a graph, draw your curve line over the graph in a rough estimate, just to help you out. But this is what people will typically do, right? So to answer the question, if we're trying to figure out how much of the curve is below z equals negative 0.78, again, that would be 0.78, but on the left side. Let's take a look. So what people usually do is they will draw their distribution curve, and then they will shade in an area that we're interested in measuring from the position of z towards the end of the curve on the left side. So in this case, we would find that 0.78% on the left side. We would mark it down for z, and we would shade towards the left. We would shade in the interested part. Is the shaded area smaller or larger than half the curve? Remember, we talked about this. If the shaded area is smaller, look in the smaller portion column of the table. If the shaded area is larger, look in the larger portion. In this case, the area shaded is smaller than half. We'll look into the table and find 0.78 under the smaller portion section, right? Let me just zoom in here just to help everybody out a little bit. Right, we'll look into the table and find 0.78. Let's find that. Uh, 0.78 in the so we find the z-score of 0.78. We have that number, our x, and then we find the smaller portion comparator to that. So that would be 0.2177. Which makes the area in the portion that we're looking at that number, or 21.8% rounded up. People sleeping less than 6 hours per night, right? So to the left of z, again, how many people are sleeping less than 6 hours? That would be our 21.8%. And that just leaves how many people are sleeping more. We can find that on the larger portion on the table, or just do the math. That would mean that 78.2% of people sleep more than that. So again, 21.8% is referring to the area below our score. People that sleep less than our amount, and 78% is the score above, people that sleep more than that amount. So we have the answer to our first, to that question. And let me just close a tab here, make things a little bit easier to follow for the people that are, but what if we wanted to convert z-scores to raw scores, right? We're not just converting raw scores to z-scores anymore. So how do you get raw data, raw scores from z-scores? Let's say we have another z-score sample of -2, 0, and 2. And we want to determine our raw scores corresponding with that. Our formula would simply be x is equal to the mean plus z times standard deviation, right? So, the two operations are you have your mean and you have z times standard deviation, you're adding those together. So for all of those numbers, when it comes to the z-score of -2, that would be 6.88. Remember, we have our value, we have our mean, plus -2 times 1.126. That would mean that x is equal to 4.63. So that is our raw score, right? When it comes to 0, -6.88 times, or plus anything times 0 is just going to be that number. And then for the z-score of 2, 6.88 plus 2 times 1.126 would be 9.13. So our raw scores through the conversion there would be 4.63, 6.88, and 9.13. We understand that. Now let's go and let's apply that to the question that we were looking at before, right? Returning to the question. Applying that knowledge, right? Remember, the question from the sleep data was how many hours of sleep represent the 5th percentile. In other words, at how many hours of sleep do 5% of people get less sleep than that, right? Let's pretend that we didn't know the z value. First, we would need to determine what z value corresponds to 5% in the smaller portion, right? Because we are trying to find how many hours do 5% of people the wording of that question is so weird, bro. Okay, how many hours of sleep represent, yeah, okay, so how many hours of sleep represents the 5th percentile? In other words, at how many hours of sleep do 5% of people sleep to get less sleep than that? Jeepers. Okay. Yeah, so, as far as application goes, let's determine what z-value corresponds to 5% in the smaller portion or 95% in the larger portion. So we would find 0.05 in the smaller portion, right? Again, we don't have our original z-score. We don't have the ability to convert that yet. So again, remember the question is just asking for the percentile. We don't have a number, right? Before, in our other question, we were given our value of 6. Now we don't have that number. So how would we do this? Right, because we don't have our z-score. We would need to find the z-score based on the larger, smaller portion. So we have our percentile. So we're going to find, again, 0.05% in the smaller portion or 0.95% in the larger portion. It doesn't really matter that much. And if we look, where do we find 95%? Oh boy, this is the issue here, where we find 95% or 0.5% and its corresponding z-score. If you look at the screen right now, it is equally distributed on either side. So there are two equally as accurate answers. Again, if we look at the columns, the z-score of 1.64 has a smaller portion of 0.05.5, or 0.0505, and the z-score of 1.65 has a smaller portion of 0.0495. Naturally, we're looking for a smaller portion of 0.5, and again, both of these z-scores have smaller portions that are equally as far away from it. So they're both equally as close to 0.05. Therefore, what do? We just split it in half. We don't split it in half, but we find the half. The approximate z-value, we're battling between 1.65 and 1.64. We just take a plus or minus z-score of 1.645. Right? Is it plus or minus? Well, let's see. We're looking at the 5th percentile, which means the bottom 5% of sleepers, right? 99th percentile would be the top, 5th percentile would be the bottom, which means it's a low value, which means it's less than average. What do we know? We know that when it is less than average, it has to be on the left side, just like a number line. That makes it negative, right? That means less than, that means that our value is less than the mean, which must be negative, so our approximate score is negative 1.645. So now we have our z-score. Now, again, the question, how many hours of sleep, what is x, right, represents the 5th percentile. So we found our 5th percentile in the table, we found our z-score off of that, and now we convert the z-score into the raw data, right? We convert it into a raw score. So remember our formula, x, the number that we're looking for now, equals the mean plus our z-score times standard deviation, right? And we have those numbers. They were given to us in the question, the mean, the standard deviation again. So x would be equal to 6.88 minus what is 1.85, which is 5.03, which means if we round, 5% of people, well, if we don't round, I guess we want to keep it right now, but 5% of people, right, that number that we're looking for, get 5.03 hours of sleep or less. That is our x number. So we've managed to solve that question. So the wrap up here, right? Normal distribution is bell-shaped symmetrical. It's a theoretical model of real-world data. The empirical rule is a prediction in proportion to a first, second, or third standard deviation, simply formed with the 68, 95, 99.7 rule. And then I guess we'll go with that. The z-score is the number of standard deviations a value lies from the mean, and the formula is the x value minus the mean over the standard deviation. The raw score from the z-score converts z back to actual data units, right? So that would be x is equal to the mean plus the z-score times standard deviation. And the percentile, generally just what we're looking for, is the percent of values below a given score, right? So the area under the curve from the z table. Those are our, that's kind of the concepts that we're working with through this entire chapter. The implications here. In psychology, normal distribution and z-scores are foundational because many traits, things like IQ, anxiety, reaction time, and height, approximate a normal shape generally, right? There's a broad average, and then there are extremes on the other side. Inferential statistics like t-tests, ANOVA, regression, they rely on normality assumptions. And z-scores allow psychologists to standardize comparisons between tests and population. For example, if your z-score on a depression inventory is +2, that means your score is 2 standard deviations above the mean, higher than 97.5% of respondents. Those are psychological implications. The summary of the core takeaways here, again, the normal distribution is central to inferential reasoning. The empirical rule lets us estimate probability values. Z-scores standardize and compare across different variables, and Z-tables provide the bridge between raw data and probability. Understanding these principles is crucial for interpreting research findings, assessing percentiles, and making predictions. So that is all of that. But I had written up, just because I know that this is a little complicated, a general reinforcement. Right. So let's go over just one more time what exactly it is that we're looking at when we're comparing the empirical rule and z-score usage. Like I said earlier, we're still trying to find the same kind of thing, the area under the curve, right? But the method changes because the empirical rule is a rough shortcut for typical whole number standard deviations, while z-score and z-tables are the precise mathematical tools for use for any specific value, even ones like, the 5th percentile, right? So in particular, what we're doing with the empirical rule is we are working on nice rounded standard deviations, right? What percent of people are within 1 standard deviation? What percent of people are between the mean and 2 standard deviations? What percent of people are more than 1 standard deviation above average? And we use the 68, 95, 99.7 rule to establish that. And then within 4 standard deviations, technically you would be at 100%, but it's, so that's essentially what that is. It's an approximation tool. It stops working if your question isn't exactly 1 or 2 or 3 standard deviations. What percent sleep more than 8 hours, right? In that question, it can work, right? Where all we need to do is find where the 8-hour mark is and then see who sleeps above that. In some questions, that might perfectly map out. If 8 hours is effectively right at 1 standard deviation, like it was in ours, then we can use the empirical rule. But if we ask about, what about who sleeps more or less than 6 hours of sleep? That doesn't fit standard deviation perfectly. It's kind of almost 3/4 of a standard deviation. Or what about, like we looked at what sleep time marks the bottom 5% of sleepers. That's nowhere near one of the neat 1 or 2 or 3 standard deviation points. So the empirical rule can't really account for that because it only gives you a rough estimate for whole number standard deviations. That way, when that happens, we switch to z-scores and z-tables. So with that, we're doing the same thing conceptually. We're finding the area under the curve of the probability, but we're doing it more numerically and more precisely. So when we're converting raw scores to z-scores, again, it's z equals the value we have minus the mean over the standard deviation. So in this case, for the 6 hours of sleep, it's as simple as, 6 minus 6.88 over 1.126, negative 0.78 is what the z-score would be. Then step B, we use the z-table. We look it up and we find the exact area to the left of that, right? So we would end up with 0.2177. And so we could find that about almost 22% of people sleep less than 6 hours, right? So the difference is that the purpose of the empirical rule is quick estimates, z-score is exact probability. Empirical rule works best with standardized deviations, and the z-score and the z-table work for any kind of standard deviation away. The precision in the empirical rule, again, it's more approximate, more rounded, while the z-score is exact. The input for empirical rule is simply just the range in standard deviations, while at least that's what you can put into the empirical rule, while with the z-score it's any raw value. And the output for the empirical rule and the z-score are both the percent area. Again, they're giving you the same thing, but they can be applied differently.